Okay, guys, so lesson 7, gas laws, continuation. The previous lesson talked about the combined gas law when nothing is constant and pressure, temperature, and volume are changing. These laws, the Boyle's law, Charles's law, and Gay-Lussac's law, apply to when we actually change one of those variables, either pressure, temperature, or volume. So our objectives for this lesson are to examine the 3 gas laws and apply those laws to gas problems. All right, so when we talk about keeping either the pressure, the temperature, or the volume constant, then we look at the first gas law, which is Boyle's law, and that is at constant temperature. Now, when we calculate or try to set up a problem, we say to ourselves, all right, we're going to use the combined gas law equation up here, okay, but we take out the variable that is held constant. Okay, or that is not actually indicated in the problem itself. So let's look at an example. For Boyle's law, okay, we look and say the volume, the question is the volume occupied by a gas at STP is 250 liters. The question asks what is the new pressure, or what pressure in atmospheres will the gas occupy 1,500 liters if the temperature is constant. So they tell us the temperature is constant. Therefore, we have to set up our combined gas law equation without the temperature. So we take that out like I did up here. Okay, so we set it up without the temperature and we just plug in what we have. So pressure 1 is the standard pressure, which is 1 atmosphere, because they ask for atmospheres, not kilopascals. The volume is 250 liters. We're solving for the new pressure because it says at what pressure. So we're solving for P2 at this volume, 1,500 liters. Okay, so the P2 then is equal to 0.167 atmospheres. Another example is decreasing pressure on a marshmallow. It will actually increase the volume. So have you ever actually put a marshmallow in the microwave? You're decreasing the pressure. Okay, you're allowing it to expand, therefore the volume is going to increase. Now let's look at our inverse relationship here. And this is something you're going to have to memorize. Boyle's law is held at constant temperature, and when we look at volume versus pressure and the temperature is held constant, it is an inverse relationship. So as pressure is increasing, okay, the volume is decreasing. Or if we decrease pressure, the volume is increasing, just like we said in this example. So what I'm going to do is I'm actually going to highlight this for you guys so you know that we have to memorize this. Boyle's law is at constant temperature. Okay? So let's go to the next law, and that's going to be Charles's law. And Charles's law is at constant pressure. All right? So again, same setup, P1, V1 over T1. P2, V2 over T2. But at constant pressure, we're actually taking out the pressure, and it's going to be V1 over T1 equals V2 over T2. Now let's look at the relationship. As temperature increases in Kelvin, remember when we deal with these equations, temperature has to be in Kelvin. The gas volume is going to increase, so we have a direct relationship. So Charles's law at constant pressure, again, you have to memorize this, so we're going to highlight it. And we'll do this one in blue, Charles's law, constant pressure. All right, and then let's do blue. The example, the volume of an ideally behaving gas is 300 liters at 227 degrees Celsius. What volume will the gas occupy at 27 degrees Celsius when pressure remains constant? Okay, so they're telling us pressure is remaining constant. Then I have to study and say to myself, what law does this follow? This is Charles's law. All right, so I'm going to set this up. Volume 1 is going to be 300 liters. Okay, over the first temperature. Now 227 needs to be converted to Kelvin, so we're going to add 273, okay, and get 500 Kelvin. All right, now that's going to equal the new volume, which we're solving for, over the temperature, which is 27 degrees, convert that to Kelvin, and we get 300. All right, so we're going to put 300 Kelvin over here. Now cross multiply or divide this out, multiply by 300, and you actually get, this is incorrect in your notes, okay? This is based on leaving it at degrees Celsius, which is incorrect, okay? It has to be in Kelvin when we do these equations. So your answer is going to be 180 liters. Another example here, and real world example, aerosol cans, okay, if you use them anymore, with gases under high pressure can't be near high temp, or the contents will expand and the bottle will explode. So if you've ever had a chance, and I don't know if you have, but if you throw maybe a can of shaving cream in a fire pit, it's going to explode and you'll hear it. It will sound like a bomb almost, okay, because the gas is expanding and it's going to expand with so much pressure that it causes the bottle to burst. Okay, so the next law is Gay-Lussac's law, which is at constant volume. So again, let's highlight what we need to highlight here. Okay, Gay-Lussac's law, constant volume. Again, you need to study these, memorize them, whatever you have to do to get yourself to know them. Okay, again, direct relationship now. So the only one that's inverse is Boyle's law. You have to know that. Direct relationship for Charles's and Gay-Lussac. So as pressure increases, temperature is increasing at a constant volume. So here's an example. The pressure exerted by an ideally behaving gas is 700 kilopascals at 200 Kelvin. So we have good temperature units here. What pressure does the gas exert at 500 Kelvin when volume remains constant? So what we're going to do is set up our equation. And now we know constant volume, so we're taking out the volume here. So now it's P1 over T1 over P2 over T2. All right? So now we're going to set this up. So we have 700 kilopascals over the first temperature, which is 200 Kelvin, is going to equal P2, what we're solving for, over 500 Kelvin. Punch this into your calculator, divide 700 by 200, multiply by 500, and this is your final answer, 1,750 kilopascals. All right, so let's look at some sample problems to help you out and to apply. So if you go back, actually, this one is a repeat of what is on page 21 in your notes. And we've done this one already, so we're going to skip that. But let's go to number 2. The volume of a sample of gas at 273 degrees Celsius is 200 liters. If the volume is decreased to 100 liters at constant pressure, what will be the new temperature of the gas? So constant pressure is Charles's law. And we're going to use the equation V1 over T1 equals V2 over T2 because we took out the pressure. Now let's set this up. Volume is 200 liters over our temperature converted to Kelvin is going to be 576 Kelvin. Oh, I'm sorry, 546. 46. Okay, and then our new temperature is what we're solving for, and the volume is at 100 liters. So we calculate and we get T2 is equal to 273 Kelvin. Okay, next problem, what will be the new volume? So we're looking for V2 here. If temperature and pressure are both doubled. So we're going to use our combined gas law here to show the relationship of what happens when we double both the pressure and the temperature. So what we're going to do is, actually, if you punch in all of this and we just give a theoretical number, anytime we double the pressure and the temperature, the volume is actually going to remain the same. It's actually going to stay the same in this case. So always stays the same when we double temperature and pressure. Okay, so if you think about it, temperature and pressure are both going to be doubled, so that cancels out, the volume has to be equal. Okay, so number 4 asks about the temperature after volume and pressure have changed. Okay, so again, now this is everything, so it's a combined gas law, P1 V1 over T1 equals P2 V2 over T2. All right, so we're going to set this up. We have 330, and torr is okay as long as we keep the units constant. Just temperature has to be in Kelvin, which it is. So it's 300 times 400 milliliters over 298 Kelvin equals, and then it says at what temperature, so we're solving for T2. And then we have 200 milliliters at 660 torr, and I'm not going to put the units because I'm running out of space. okay? But we'll do it it's going to get canceled out anyway. So our T2 is equal to 298 Kelvin. Look at that. So what we did was we actually doubled the pressure and the temperature remained the same. It didn't change. All right? So that's it. That concludes lesson 7. I'd like you to do some practice. So on page 14, it uses Avogadro's law, and I'd like you to apply that law to the questions on that page.